Dear children, we have already started with solution chapter, and in this chapter we have done different ways to express the concentration of solution, solubility of gases and liquid, which is given by Henry's law. We have also done Raoult's law, which is about the vapor pressure of liquid solutions. And in the last class we have done ideal and non-ideal solution. And in today's class we are going to discuss about the properties of solutions. As we have the properties of solids, liquids and gases, the same way we have the properties of solution. Which property of solutions we are going to discuss? Colligative property. What are colligative properties? Colligative properties are those which depend only on number of particles of solute and are independent of nature of solute. They depend only on number of particles of solute and do not depend upon the nature of solute. I'll explain it further later on. There are four colligative properties which we are going to study. One is it is relative lowering of vapor pressure. Second is elevation of boiling point. Third is depression of freezing point, and fourth is osmotic pressure. These all colligative properties we are going to study when we add non-volatile solute to the solvent. Let's talk about the first colligative property. First colligative property is relative lowering of vapor pressure of solvent. Before starting with this, I'll discuss what happens to the vapor pressure of solvent when a non-volatile solute is added, because we'll discuss all colligative property in context of the solution which contains non-volatile solute. So let's see, if you have a container in which some liquid is there, only solvent is there, which is A. It is a closed container. Whole of the surface of liquid is having only the solvent molecule, and all solvent molecules are volatile. They'll undergo evaporation. After some time, condensation will also start, and a stage will come when rate of evaporation becomes equal to rate of condensation, and some vapors are formed over the surface of liquid. The pressure exerted by the vapors, the equilibrium vapor pressure which is exerted over the surface of liquid, is called as the vapor pressure. Now, when I take the same container, there is already a solvent which is A, but I also add B, which is non-volatile solute. Now the surface is occupied by both A and B. From A, the evaporation will take place, but from B, as it is non-volatile, evaporation will not take place. And it is also a closed container. Naturally, the rate of evaporation decreases and vapor pressure also decreases, because now the escaping tendency is less. Evaporation is a surface phenomena, vapor pressure is also a surface phenomena. Now some part of the surface is occupied by non-volatile solute, so enough vapors will not be formed at the same temperature. Shall I say there is lowering in the vapor pressure of the solvent by addition of non-volatile solute. Who is non-volatile solute? Which doesn't undergo evaporation. Maybe it is sodium chloride, or it is sugar or glucose, something like this. So let's talk about this colligative property, relative lowering of vapor pressure of solvent. According to Raoult's law, we know that partial pressure of A component, when it is present along with B, because it is lesser vapor pressure, is directly proportional to its mole fraction. more the number of moles of A component, more is its vapor pressure here. So I can write down P is equal to P naught A XA. What is PA? Partial vapor pressure of A component when it is present in the solution along with B component. What is P naught A? P naught A is the vapor pressure of A component when it is present alone. It is the vapor pressure of pure component A, which is here, when it is present alone. And mole fraction of A is written by XA. I can write down this as PA is equal to P naught A, and XA can be written as 1 minus XB, because we already know that XA, because we know that XA plus XB is equal to 1. I can say PA is equal to P naught A minus P naught A XB. I can further write it as, I'll take this quantity on this side, this becomes P naught A XB, which is equal to P naught A minus PA. This is P naught A minus PA. I'll say XB is equal to P naught A minus PA upon P naught A. Just reversing the two sides, I can write down P naught A minus PA upon P naught A is equal to XB. See, what is this? P naught A is the maximum vapor pressure of A component, pure component A, when only A component is present. So it is the maximum value of vapor pressure, but when non-volatile solute is added to this, this becomes PA, which is definitely less than P naught A. So shall I say there is lowering in the vapor pressure of A component when non-volatile solute is added to this? So this one, P naught A minus PA, this is called as lowering in vapor pressure. Vapor pressure of solvent decreases when you add non-volatile solute, and when you divide it by the maximum value of vapor pressure of A, this becomes relative lowering in vapor pressure. In relation to the maximum value, this is the lowering in vapor pressure. So whole of this term is called as relative lowering in vapor pressure. And XB you already know, it is mole fraction of B component, that is solute. What kind of solute? It is non-volatile solute. I can write down this expression as P naught A minus PA upon P naught A is equal to XB can be written as number of moles of B upon Na plus Nb, total number of moles of solution for very dilute solutions. If the solution is very dilute, then we can always neglect Nb in relation to Na. Nb is very, very less than Na, so we can neglect Nb. Not here in the numerator, but only in the denominator, because here it is in addition to A. In comparison of A, B is very, very small, so here it can be neglected. So it becomes here P naught A minus PA upon P naught A, which is equal to Nb upon Na. It can also be written as, Nb can be written as given mass of solute B divided by molar mass of solute, and Na can be written as Wa upon Ma. So I'll say P naught A minus PA upon P naught A is equal to Wp upon Mb, Wa upon Ma. This is one more expression of this colligative property. Why do we say it is a colligative property? Relative lowering in vapor pressure is a colligative property because it is depending upon the number of moles of solute. It depends on the number of particles of solute, and it may be of anything. Maybe it is glucose or it is fructose, sucrose. So it is independent of the nature of the solute. So if 1 mole of glucose and sucrose is added, then they will show the same amount of relative lowering in vapor pressure. What is the utility of studying all these colligative property? Utility is to determine molar mass of solute. How will you determine this? Just take molar mass on this side and relative lowering in vapor pressure on this side. So MB can be written as WB into MA upon WA into P naught A minus PA upon P naught A. So this is there. In this way, we can always find out the molar mass of solute if we know the given mass of solute, molar mass of solvent, and given mass of solvent, as well as the value of this colligative property. This is about the first colligative property. Let's move to the second colligative property of solution. Second colligative property is elevation of boiling point. Of solvent. But before that, I'll discuss what is boiling point. Again, I'll take a container. Some solvent is taken into this and it is a closed container. I'll start heating it. After some time, some vapor pressure is exerted over the surface of liquid. At a particular temperature, vapor pressure becomes equal to the atmospheric pressure. What is atmospheric pressure? It is 1 atm. So when the vapor pressure becomes equal to the atmospheric pressure, all of you know vapor pressure is exerted, it moves in the upward direction, its forces in the upward direction, whereas atmospheric pressure is exerted in the downward direction. When the two forces balance each other, then liquid starts boiling. What is the relation of this pressure with the boiling point? So this is the temperature. How will you define boiling point? The temperature at which vapor pressure becomes equal to atmospheric pressure. When that temperature is responsible for creating sufficient vapor pressure which becomes equal to atmospheric pressure, and the liquid starts boiling. So how will you define boiling point? Boiling point is the temperature at which vapor pressure of the solvent becomes equal to the atmospheric pressure. What happens when I add non-volatile solute? Initially it is only A component, and now I'll take another container. I have taken A, which is solvent, maybe water. I'll add some non-volatile solute. We are studying all colligative properties by addition of non-volatile solute. Again, it is a closed container. I'll heat it. Initially when I heat it, vapor pressure may not be enough because now the surface is also occupied by non-volatile solute. We all know the boiling temperature of water is 100 degrees Celsius. So at that temperature, at 100 degrees Celsius, vapor pressure may not be enough because now the surface is occupied by non-volatile solute. Vapor pressure may not be equal to atmospheric pressure. So you need to heat it more so that the vapor pressure becomes equal to atmospheric pressure. And when you heat it more, then boiling point is raised. So shall I say there is elevation in boiling point of the solvent by addition of non-volatile solute. Who is a non-volatile solute? Sugar, sucrose, glucose, fructose. These all are there, or maybe the other salts are also there. Sodium chloride, copper sulfate. These all are non-volatile. With the help of graph also, we can understand this elevation of boiling point. If I plot a graph between vapor pressure on the y-axis and temperature on the x-axis. It is expressed in Kelvin. We already know if I raise the temperature, vapor pressure increases. So the graph is something like this. So if I increase the temperature, vapor pressure keeps on increasing. And this I'm talking about pure solvent. You know, vapor pressure increases 0.1, 0.2, 0.3, 0.4, and a stage will come where vapor pressure becomes equal to 1 atm. This is the pressure where it is equal to 1 atm. So if I keep rising the temperature, vapor pressure keeps on increasing, and a stage will come when it reaches to 1 atm. And this point, at this temperature, the liquid will start boiling, and this is written as TB. I'll write down, this is TB, boiling temperature of pure solvent. So I'll write down TB naught. What happens when I add non-volatile solute? So naturally solution has lesser vapor pressure at the same temperature. So I'll plot a graph below this graph, but the relation is again the same. If I increase the temperature, vapor pressure also increases. So I'll increase it and vapor pressure is also increasing. When I increase the temperature, vapor pressure is increasing, but at this temperature where the pure liquid has started boiling, it is not the boiling point of solution. We need to increase the temperature so that the vapor pressure becomes equal to 1 atm, and it will increase and it will touch 1 atm pressure at this point, and corresponding to this the temperature is called as TB. It is the boiling temperature of solution which contains non-volatile solute. So you have seen, it is the boiling point of pure solvent, it is the boiling point of solution which contains non-volatile solute, and there is increase in boiling temperature. It is represented by delta TB. There is increase in boiling temperature. Let's see mathematically how will you say. Out of the two, which is greater? TB is greater. I'll say TB minus TB naught, which is written as delta TB. Delta TB is elevation of boiling point. It is directly proportional to molality of solution. More the number of moles of non-volatile solute, more is the elevation in boiling point. It is directly proportional to the concentration of solution. So delta TB is directly proportional to molality. Delta TB is equal to Kb dot M. Dot means multiplied. What is Kb? It is molal elevation constant. It is molal elevation constant. It is also called as ebullioscopic constant. What is M? M is molality. What is delta TB? It is elevation in boiling point. How will you define molal elevation constant? If I say molality of solution is unity, then this expression becomes delta TB is equal to Kb. So Kb is equal to delta TB. So we'll say molal elevation constant is defined as elevation in boiling point when concentration of solution is 1 molal. I repeat, molal elevation constant or ebullioscopic constant is defined as elevation in boiling point when the concentration of solution is unit molal. This expression can further be written as delta TB is equal to Kb, and molality can be written as number of moles of solute dissolved in given mass of the solvent, and if it is expressed in grams, it has to be converted into kg. So our formula is delta TB is equal to KB into number of moles can be written as WB upon MB into 1000 into WA in grams. Elevation in boiling point is a colligative property because delta TB is directly proportional to number of particles of solute, number of moles of solute. And it is irrespective of the nature of the solute. It may be glucose or fructose or sucrose, but it depends only on number of particles of solute. So it is a colligative property. What is the utility of colligative property? Again the same, to determine the molar mass of solute. So you write down utility of colligative property. Utility is to determine molar mass of solute. I'll write down MB on this side, and it is equal to KB into WB into 1000 divided by WA, which is given in grams, and this is delta TB. So if we know all these values, we can always find out the molar mass of solute. Is there any application of elevation in boiling point in our daily lives? Yes. During cooking, I'm not talking about when the cooking is done in pressure cooker, but if it is done in a vessel or a container or some kadhai, so you may write down in daily life, cooking will be faster by addition of non-volatile solutes such as sodium chloride, because it raises the boiling temperature of water. This is about second colligative property. Let's talk about third colligative property. Third colligative property is depression of freezing point of solvent. This is not about the depression among the people, it is about depression in the freezing point. Before discussing this, I'll talk about freezing point. At freezing point, solid phase is in dynamic equilibrium with liquid phase of the substance. So there are two phenomena which are happening here. First one is, I'll say, when liquid phase of the substance is in dynamic equilibrium with solid phase. And another, I can say, vapor pressure of solid solvent is equal to vapor pressure of liquid solvent. What is all this? When you take out the ice cubes from the refrigerator, you say they are properly in the solidified form, but that is not the freezing point. But if you take out the ice cubes slightly before that temperature, you will see, if you touch the ice, you will see that some water is underlying that solid surface. So at that stage, when solid and liquid are in equilibrium means the same number of molecules are moving from liquid to solid and solid to liquid. So they are in dynamic equilibrium. Or I may say the vapor pressure of solid solvent is equal to the vapor pressure of liquid solvent. At freezing point, both the states coexist. What are those two states? One is solid, other is liquid. When liquid and solid, they coexist, when they are in dynamic equilibrium, when their vapor pressures are equal, that is the freezing temperature. So this is about the pure solvent. What happens when you add non-volatile solute? When you add non-volatile solute to this, what happens? Then the freezing point will be defined as the temperature at which vapor pressure of solution is equal to vapor pressure of solid solvent. What does it mean? When the vapor pressure of solution becomes equal to the vapor pressure of frozen solvent. When the two are equal, then only the freezing point of solution will come. I'll explain it graphically. Let's see. I'll plot a graph between vapor pressure on the y-axis and temperature on the x-axis. When I increase the temperature, vapor pressure of solvent keeps on increasing, and when I decrease the temperature, vapor pressure keeps on decreasing. So I'm talking about that when I decrease the temperature, vapor pressure decreases. This is the graph of pure solvent which is in the liquid state. So I'll say this is liquid solvent. This is liquid solvent. Afterwards, if I further decrease the temperature, it will change into solid state, and this will be written as solid solvent or frozen solvent. This is liquid solvent and this is frozen solvent graph, and when the two coexist, both the state coexist and their vapor pressure are equal to each other. At this stage, their vapor pressure are exactly equal. So at this stage, solvent will freeze, and this is written as TF naught. When I add non-volatile solute to the solvent, again the relation is same. More the temperature, more is the vapor pressure. Lesser the temperature, lesser is the vapor pressure. So this is the graph for solution, and you will see if I keep on decreasing the temperature, vapor pressure also keeps on decreasing, but it will not freeze at the same point where the pure solvent has frozen. There is a need to decrease the vapor pressure of solution so that it becomes equal to frozen solvent, and it will be equal to frozen solvent at this temperature. I've said vapor pressure of solution when it becomes equal to vapor pressure of frozen solvent. So I kept on decreasing the temperature. Vapor pressure of solution also keeps on decreasing, but there is a need to further decrease the temperature of solution so that its vapor pressure becomes equal to frozen solvent. And at this temperature, freezing will take place for solution. So this is the graph for solution. So solvent has freezing temperature this much, but when you add non-volatile solute, there is a depression, there is lowering in the freezing temperature, which is written by TF, and the difference of the two can be written as delta TF. So let's talk about the mathematical expression. Out of the two, TF naught is greater. So I'll say TF naught minus TF, which is equal to delta TF, which is depression in freezing point, is directly proportional to molality. It is a colligative property. Who is a colligative property? Depression of freezing point of solvent. It is directly proportional to the molality. Molality is a term to express the concentration. More the molality, more is the depression. Lesser the molality, lesser is the depression of freezing point of solvent. I can write down delta TF is equal to Kf into molality. This is one of the expression, and you know all these terms. Delta Tf is depression of freezing point, and Kf is molar depression constant, and M is molality of solution. It is also called as cryoscopic constant. If I say molality of solution is unity, then delta Tf becomes equal to Kf. This value is 1. How will you define Kf? Kf is defined as depression of freezing point of solvent when concentration of solution is unit molal. I repeat, when the molality of solution is unity, then molar depression constant is equal to depression in freezing temperature. So I can further write this expression as delta Tf is equal to Kf. Molality can be written as number of moles of solute dissolved in a given mass of solvent, which can further be written as delta Tf is equal to Kf into Nb can be written as Wb upon Mb into Wa. If it is given in grams, it should be converted to kg by dividing by 1000, and you get this expression where, sorry, this is delta Tf. Delta Tf is depression of freezing point of solvent. Kf is molar depression constant. Wb is the given mass of solute. Mb is molar mass of solute. Wa is given mass of solvent. What is the utility of this colligative property? Again the same. Let's write down utility of colligative property. It is used to determine molar mass of solute. How will you do this? Mb you can write down here, and this comes out to be Kf into Wb into 1000 divided by Wa into delta Tf. So if we know all these values, that is Kf, Wb, Wa, delta Tf, then we can always calculate Mb. What is the practical application of this colligative property? You know, if you go to hill stations and if there is a snowfall, then it is very difficult to move in that particular area. So what do they do to remove that snow? They just sprinkle some salt, maybe sodium chloride, which is very cheap. What happens? You might have seen, if you sprinkle salt over this snow, it melts down. It is also based on depression in freezing point. What happens to the solvent? Solvent has a particular freezing temperature at which it is in the solid state. But when you sprinkle salt over it, there is a depression, there is lowering in the freezing temperature. Snow will not remain in the frozen form at that particular temperature. It will freeze at a much lower temperature by the addition of non-volatile solute. So at that particular temperature, it will melt down because it needs further lower temperature to remain in the solid form, to remain in the frozen form. It has many more applications. Please find out some more application. You might have seen that ice cream wala, rather kulfi wala, also add some amount of salt. So when you have a kulfi, this has a little salty taste. What is the purpose of addition of that? Just find out all these applications, what you see in your daily life. Although we are left with one more colligative property, that is osmotic pressure, plus few more topics of this chapter which we'll discuss in the next class. So let me summarize what we have done today. We have done colligative properties of solution. First colligative property is relative lowering in vapor pressure, because it is equal to the mole fraction of solute. So P naught A minus PA upon P naught A is equal to XB. And then we have also discussed the second property, which is elevation of boiling point of solvent, and it is used in our kitchen while cooking, and it is delta TB is equal to KB into molality of solution. And third colligative property is about depression of freezing point of solvent. It is applicable on the hilly areas to melt the snow during snowfall season. And I would like to mention just two more points about KB and KF. Although their derivation is not there in the syllabus, but there are two expressions which can be asked in the entrance examination. Both KF and KB, KF is cryoscopic constant and KB is ebullioscopic constant. Both of them, they depend on the nature of solvent. So just see the expression which is there. KF and KB, it is equal to R M1 into TF square upon 1000 into delta H fusion. I'll explain it. And this is also written as R into M1 into delta, TB square upon 1000 into delta H vaporization. R here is gas constant, M1 is the molar mass of the solvent, TF is freezing temperature of the solvent. Rather, I should have written TF naught. This is also TB naught. TF and TB are freezing temperature and boiling temperature of pure solvent, and delta H fusion is enthalpy of fusion, whereas delta H vaporization is enthalpy of vaporization. What are the units of KF and KB? Both of them, they have unit Kelvin per molal. Kelvin per molal. So it should have been written rather Kelvin molal minus 1. So children, this is about today's lecture. In the next class, we'll discuss the rest of the topics. Hope to see you again.